you'd be hard pressed. You could call it ethyl and then something, ether, right? But we're starting to get a little more complicated where that's not probably the best way to deal with it. So what you do is you treat this guy as a substituent. And let's put a bromo on it. Tack a bromo on. Okay, so as a substituent, there are 2 carbons, so F, this is an ethoxy substituent. So your substituents are alkoxy groups, and whatever that alkyl group is you put oxy in. Okay, so that's an ethoxy group. It's alphabetized under E. So, in terms of numbering this thing, 1, 2, 3, I think we'll be going that way. What do you guys think? Okay? So, number it. 1, 2, 5, 6. All right. So this would be 2 bromo. And then we have ethyl at number 4 and ethoxy. Which wins?
Ethoxy.
Ethoxy. Good. So 3 ethoxy, 4 ethyl, hexane. All right. Let's try a different one. See what you come up with for that. And then the next one has a complex constituent. We'll work on that one together. Just write it down. As far as this one. Oh, yeah, okay. The parent, let's just circle it. Coming in through here, and then up. Like that. Now I didn't go straight across, because that didn't have as many branches as going up. Because this thing counts as a branch. So, what is the parent in this? Is it the parent functional group? Is it the alcohol, the alkene, or the ether? No. It's the alcohol, right? The ether is just a substituent. Okay, so we have 1, 2, 3, 4, 5, 6. All right. There's a methyl substituent at 5, and then what can I call this group right here?
Sec-butoxy.
Good. Sec-butoxy.
Okay, that's a problem. Is it pro?
Yeah. You could name it ibuprofen. It would be propoxy without that methyl there, right? So it is 1 methyl propoxy.
For
So do that too.
For isopropyl would be isopropoxy.
Isopropoxy, exactly. Isopropoxy, that sounds a little weird. Okay, so here we go. So we we have 6 sec-butyl
Butoxy.
butoxy, 5-methyl. And now this thing just names like an alcohol with an alkene in it. So how do I do that? X, 3, ene, 2, all, and I'm not quite done. E. Yeah. You could stick the E since I left no space. We'll conveniently stick it out there. The E could be right behind the 3 as well. Okay, questions on that one? All right, now let's try our hand at this one. I have to choose a parent, and since I've got a functional group in there, it helps. This is going to be the parent, this chunk up here. And this is going to be the substituent. Everyone okay with that? All right, so now in terms of selecting the chain, here, here, and then up.
So it's dimethyl.
All right. Now we have to name that nightmare of a substituent. The dimethyls are easy. We have to do this thing right here. So we have a couple of options. There's obviously no common name. So let's take a look at the 2 options that are available. Hey, Rick.
Oh, no, I was
No,
just gonna say.
the first one would be the old way. And under the old way, the point of attachment is considered to be number 1. Right? That's the old way. And then we find the longest chain, well, 1, 2, 3, or the other way, 1, 2, 3. Either way, it's the same, right or left. This one has a substituent, so that's what I would choose. So under the old way, what I'm going to call this would be 1-ethyl, 2-methyl, propoxy. Okay, that's old. The new way is a little bit weird, and I think I actually plugged this into ChemDraw to help me out. Just doing the ending is kind of weird. Under the new way, if you remember, you don't start the numbering necessarily at the point of attachment. The point of attachment just gets the lowest possible number, and you choose the longest chain. So, the new way, what I'm going to do is I'm going to say, okay, there's my longest chain. The point of attachment, I'm going to number the chain so that gets the lowest number. So starting from here, 1, 2, 3. Starting from here, 1, 2, 3. That didn't help. It doesn't matter which end I start from in terms of the point of attachment. So then I look at the substituents. I want the methyl to be a 2 versus a 5, or 4, whatever it would be. So I'm going to go 1, 2, 3, 4, 5. So under the new system, this is what this thing is. 2-methyl. And then, there are 5 of them. So it's pentan, 3-eel, and then they put an oxy at the end. Isn't that weird? That was the part I had to go get help on. That's how they deal with the new nomenclature. Yeah.
That's branch kind of looks like the bicep branch. Kind of
Over here,
Yeah.
right here, you know, it looks like sort of like an isopropyl. If you were to do that though, you would have to then mix IUPAC and common nomenclature, and you don't. Once you're into a system that's complicated, you have to go IUPAC.
As a hexo.
Yeah, no, maybe like an isohexyl or something. Yes.
Just for use, we had alkene or double bond between 1 and 2.
Okay.
In the new way, it would be pen.
Yeah, Aaron's asking, what if you did something like that? Like that, right?
Yeah.
Okay. Assuming that this guy still is my parent, that I didn't alter that, how would we deal with that? We would call it 2-methyl, and then it would have to be, instead of pentan, it would have to be pent, 1-ene, would go right there. Instead of an, it's an e. Okay? Yeah.
Is it pronounced oxy?
If I were going to pronounce that, I'd do 2-methyl-pentan 3-eloxy. Eloxy. Eloxy. Yeah. Not pretty. This the old nomenclature system looks a little nicer to me. Okay. Yeah.
If you put like OH on the substitution, would that then become the parent chain?
Exactly. Yes. Let's say I did this. If I put OH there, then things switch around. This is the group that wins over all of them. Then this becomes the parent, and I'd have to name that as a substituent. And it would switch over because the OH has priority over everything else. Okay? I've got this so messed up now. We have to actually name it, and I don't remember what it looked like. I think it was that. Is that right?
Is that?
All right, let's name it. Okay, this top name is 1, 2, 3, 4, 5, 6, 7. Okay, let's, depending on which system you use, new or old, it's going to affect your alphabetizing. So I'm going to use the old way and file it under E. If you use the new way, it's going to go after the methyls. This would go after the methyls. This would go before it. Okay? And one's not wrong, you just have to be consistent. So we'll go the old way of doing it. So we have at number 4, all this junk. 1-ethyl, 2-methyl, propoxy. And then it's just naming the thing like normal. So it becomes a 5,6-dimethyl. There's 7, so we have 2-E. The new system, you'd still have the 4, but this would start then with an M, and it would throw it there, right there. All right? All right, let's look at physical properties of ethers. With an ether, let's just look at dimethyl ether. What's the hybridization of the oxygen? sp3. Good, it's sp3. So everything's based on a tetrahedron. And I'm going to put a CH3 here, CH3 there, lone pairs. So this angle is about 109.5. But you can't see the lone pairs, right? So what's the geometry of an ether, the actual molecule? It's bent geometry. So we have bent molecular geometry. And the bond angle, roughly 109.5, squeezed down a little bit by the lone pairs. Okay. Very similar to water in how it appears. One of the key things about an ether is that there is no hydrogen on the oxygen. So, guess what it can't do?
Hydrogen bond.
It can't hydrogen bond, exactly. So since it can't hydrogen bond, it's a polar molecule though. So let's make a note here. Since it can't hydrogen bond, it's got London force, low melting point. Exactly. It's got dipole-dipole. So what you see with these guys, low melting point and a low boiling point. So just to give you an example, here is butanol. And it's got a boiling point And if I take a look at the isomer, same mass, but diethyl ether. Okay, so the mass is the same, they're both polar. This has a boiling point of 34.5 degrees. Makes a giant difference. So ethers boil off pretty easily, and that's one of the reasons that we use them in extractions. That's actually really convenient. You can boil off ether easily, and so it's good for extractions. If you remember back to Chem 420, when we do an extraction, we took something, caffeine, let's say, in an aqueous layer, and we added an organic solvent that was not soluble in the water. So you get your two layers, and remember you shook, and hopefully you didn't get an emulsion, and it transfers the whatever you want out of the water into the solvent, right? And if your solvent is really hard to boil off, then you take the solvent plus your caffeine to the hood, and you heat it, and you heat it, and you blow air on it, you heat it. It can take you a really long time. So ideally, you want a solvent with a pretty low boiling point that can dissolve a lot of organic things. And that's ether. It dissolves a lot of organic materials, but because it boils off really easily, once you've used it, you can get rid of it really easily. It boils off like that. And so that's where we see them a lot, is extraction solvents as well.
Would it be harder to actually get this more dynamic products because it just boils off for you?
You know what it is. If you were to use it as a solvent that required where the reaction required high temperature, it wouldn't work.
Yeah.
That'd be bad. Like the one we use xylenes in the Diels-Alder. Ether would be a poor solvent for that Diels-Alder reaction because you could never get it above room temperature very much. So you do have to be careful about that. But something like the Grignard, you know, it worked great. Yeah. Okay, one of the things about ether is when you do an extraction, and you go and you smell the water layer after you're done, let's say you do a superb job at separating the two layers. So visually to you, there is no ether in the water. You've managed to get it all away from the water, and it looks like a picture-perfect separation. If you go and you smell the water layer, it smells really strongly of ether. And what's going on there is ether cannot hydrogen bond to itself, but ether can accept hydrogen bonds from other things. Or let's just put from other compounds. And the biggest example of that is water. So, if you have ether, I have O, I have R, let's just do that. And I have water I'm mixing with it. This hydrogen, remember, has a big delta plus, and that's what made it want to hydrogen bond with things. So this hydrogen could find another water molecule and hydrogen bond with it. Or if you mix the water and the ether together, this hydrogen could come over and it could donate a hydrogen bond to ether. Ether can't offer a hydrogen bond back. Okay, it's not a hydrogen bond donor, but it can be a hydrogen bond acceptor. And what that means is that ether is about 5% soluble in water. So even if your extraction is picture perfect and you have mechanically separated the layers, there's still some ether dissolved in that water because it was able to get in there by getting hydrogen bonded too. That's why it kind of smells. Okay, the last characteristic of ethers, of hydrogen bonding, is that they are inert to most reactions. So let's put some numbers on this. I'm reading back. Make this number 2. Make the bond angle thing number 1. Characteristic number 3. They are inert to most reagents. As we'll see in just a minute, there's a reason they don't do very much. And as we go through reactions, the reaction, we'll see why that is. I saw a hand up somewhere. No problem solved. Okay. All right. Let's go ahead and talk about synthesis. There are a couple of ways to prepare ethers. This first one is the most generic, and it's what's used in industry. So we can call this industrial prep. And it's only good for what are called symmetrical ethers. So it has some limitations to it. And what I mean by symmetrical ethers is that these R groups, here and here, they're the same. So they both have holes, they're both metals, whatever. This industrial prep involves taking two alcohol molecules, mixing it with an acid catalyst in the form of usually concentrated sulfuric acid. And you end up forming your ether and water as a byproduct. I think that's the byproduct. Am I going to get myself in trouble? Nope, I'm good. Okay, let's go ahead and look at the mechanism. And then we'll talk about what the limitations are. And let's use a real molecule. Let's use propanol. So in the first step, we're going to be adding the acid catalyst to one of the alcohol molecules. And this is something that you guys have seen before. In the alcohols chapter, we did this pretty frequently. We protonate the OH. And that gives us OH2. And it's a good leading group, exactly. So now I've got a decent leading group, and I have more alcohol around. So I'm drawing my second propanol molecule. And here the oxygen is going to act as a nucleophile. It's not a superb nucleophile, it's okay. I've got a really good leading group, so that balances it out. And it attacks the primary carbon and kicks out water. So I have that and water. Now to help orient you as far as what's where, let's just put a box around the group that attacked. This is the alcohol that attacked. So that is that alcohol right there. Okay, we're almost done. The acid is a catalyst. And remember, catalysts are not used up in the reaction, we get them back. So I need H plus to come back to me. Also, to get my ether, I need to deprotonate this. I need to get rid of that. Well, I have base around. I have HSO4 minus. And so that's just what grabs off the H plus. And you end up with dipropyl ether in this case. Really like a simple synthesis. And it is under the right conditions. So, let's talk about what those are. As far as limitations, the first one, probably the major one, and one of the two major ones, is that, as I mentioned, it's for symmetrical ethers. Now, in order to see why that might be, imagine that I tried this. I took propanol, I mixed it with ethanol, and I possibilities, right? The chemicals don't care what you want. And what you have set up is you'll get some of this, right? Because I could protonate here and the ethanol could attack, or I could protonate the ethanol and this guy could attack. So I have two shots, two possible combos of getting what I want. But I could protonate propanol and propanol could attack. So I'm going to get this. And I could have the ethanol attacking itself. I can get that. So what you end up with, if you try to have the two halves different, you end up with mixtures that then you have to separate. So it's not very efficient. There are better ways. All right? Now the second limitation is that it's an SN2 displacement of water. And so what that causes is limitations on the alkyl group. What happens if you do not have primary alcohol? Let's say your alcohol is secondary or tertiary. If you have a secondary or tertiary alcohol, what you end up doing is you end up going through carbocations and you end up getting dehydration products. Okay, you end up getting alkenes. So what you'll see is dehydration. Oftentimes this reaction is done under heat, which helps to make that your major product, which is not what you want. And so what can happen if you tried it with this guy? Let's get really try it with that guy right there. What I am going to see when I mix this with an H+ catalyst and heat, well, that is all set up to give me that. And so that's a major issue. So what you really see is you see this used with only primary alcohols because they won't form carbocations very easily, and so they don't dehydrate very well. Yeah?
In the book, there was a possible way if you had a benzoic tertiary bromine and use H2O and it would affect the reaction, or would it be the same way for this?
To make an ether? Let's see, what did it look like? Benzoic tertiary, so something like, was it bromine?
It was bromine, and then you use H2O that by alcohol group, and it's going to be the same way.
H2O, that gave you an ether? Or give you alcohol?
No, I gave you an alcohol. But
Okay.
I'm saying in this case, if you had a good leaving group there.
Yeah, it could. Yes, that's actually the next one we're going to do. I think you're describing the reaction that's much more general and safer is a Williamson ether synthesis, which is an alcohol with a leaving group. Okay? You guys good on this one? This is one you probably won't use because it is so limited. You can't build anything that's interesting, and you can't have any interesting alkyl groups. So your limitations are pretty bad on this. So, much more common is a reaction that you're almost guaranteed to see on some standardized test because it's really famous. So this would be number 2. The Williamson ether synthesis. We actually showed this reaction to you guys last semester in the SN1, SN2 chapter. I don't think we ever called it this though. It would scare you. But what this is, it's really straightforward. You have an alcohol. First, you deprotonate it to make an alkoxide ion. Then the alkoxide ion, which is a good base and a good nucleophile, attacks an alkyl halide. We'll call it R prime, it's a different R group. Okay, let's make it a bromide. It attacks an alkyl halide, and it's an SN2 reaction, and you end up forming RO, R prime plus ER minus. You end up forming an ether. And your alkyl groups could be the same, or more than likely, they would be different. Okay, so that's the generic reaction. We have some more things to say about it though, that you have to kind of be careful of a little bit. But the first thing, we need to review really quickly how you're going to make the alkoxide ion. Do you guys remember a few ways to do it? Strong base, okay? So I could use, for example, NaH. Okay, that's a strong base that would do the trick. Okay, using OH minus won't be effective because it has about the same base strength as this, and so you get an equilibrium. That's not good.
What did you use, just solid sodium metal?
That's another way. So this is an or. You could use solid sodium, or solid lithium, or you could do sodium too. Sodium or potassium. Okay, either one of those would work. Okay, so the net effect is you have to make this alkoxide ion. Now let's do an example of how one of these work and talk about the choices you're going to have to make. You can't just like do it without thinking. You have to actually sit and think about how you want to design it. So let's make this. And let's put an O here. And we'll go like that. See, I want to make that either. You have to consider two possibilities when you're looking at these. The first one would be cleaving right here. So we'll call that number 1. If I do number 1, the alkoxide piece is there. So it's going to look like this, O minus. And then the other piece that's attached is the alkyl halide. Is everyone okay with that? Now I could have cleaved on the other side of the ether. I can go on either side of it. So we'll make that number 2. Could cleave right there. And if I did that, here's number 2. It's going to look like this. The cyclohexane has the halogen. And the one with the oxygen is that propyl group. You have to really think about what's going to happen with each of the possibilities. With this possibility, and remember it's an SN2 reaction. So with this possibility, I have a strong base, good nucleophile. I have a primary alkyl halide. The question you have to ask yourself really has to do with the alkyl halide. You have to know, is this a good SN2 substrate? Is it reasonable with a primary alkyl halide that I'm going to get pretty decent SN2 product? Yeah, it's like primary is the perfect SN2 thing, right? So this should work really nicely. I should be able to do this, kick that off, and get the product. So this should work well. Okay, this one over here. Look at the alkyl halide. Secondary. Okay, so it's a little bit hindered. This is a strong base. Now secondary alkyl halides, we saw they were okay SN2 substrates, not as good as primary, right? What can happen here? Good base, SN2 substrate, can do an elimination. This would show some SN2 and some E2 as well. And I actually looked up the numbers for this reaction. Yeah, got it for this one. And it turns out if you do this, you do get some product. And you also get the elimination product. It ends up up being 85% elimination, 15% what you want. Bad choice. Yeah, it's not good. So the major limitation on this is, for all intents and purposes, due to the strong base, which is OR minus, your alkyl halide, to get good yield, must be primary. That's a limitation that can cause you some trouble. It's a little better than the first one we looked at, but you have to make sure your path is good.
Is it 100% the other way?
Yeah, it's effectively, you would see almost no elimination from this. Okay? All right, now, let's say I wanted to make something that was not conducive to this. So let's say I'm in lab, and I want to make this. Like that. So it's got a lot of branching around the carbons attached to the oxygen. If I try a Williamson, which is the one we just looked at, if I try a Williamson, that would have to be my alkyl halide, which would look like this.
That's tertiary.
Or, exactly, or that would have to be the alkyl halide, this part, right? So it'd be this or this. Right? Both are bad. So I looked at this, and at your yield, the top one will never work, or the first one. The second one, you'll get probably the screaming, 10% yield, not good. Okay, so I don't want to do a Williamson on this. So the third method, this is the one you guys learned as well, is what's called an alkoxy mercuration. With an alkoxy mercuration, it's just like an oxymercuration, except for instead of water, we use an OH. So let's go over here and just review oxymercurations. So oxymercuration is where we took an alkene and treated it with mercuric acetate and water. And then the second step was sodium borohydride. That removed the mercury from it. And if you remember, this put on an OH. So it's going to add an OH. And where did it put it? Did it put it up where the methyl is, or at the other? At the top, yeah. So it put an OH right there. So it's a Markovnikov addition. And I would bet there are a number of you that are thinking, now why was that? Let's jog your memory. The intermediate looked like this. Remember this guy? Right? The mercurium ion. And the larger delta plus was at the more substituted carbon because it could be more stabilized. And because of that, that's where the nucleophile, which is water, attacked. So that's why it puts the OH with more substituted carbon. Okay, that's an oxymercuration. An alkoxymercuration would look like this. Do the same thing. Same reagents. Only the difference is, instead of water attacking, you put an alcohol in. And the second step is sodium borohydride. Same mechanism, same everything. So what's going to happen with this is you're going to end up with an OR group attached to the more substituted carbon.
Can you do categories with attack?
You know, I haven't seen that. Like where they do,
Instead of I mean, like,
the conditions for getting rid of the boron, you have, let's say here's your C double bond C, and you end up, remember, an H and a BH2,
yeah.
and then they use H2O2 OH minus. I've never seen conditions where they put an alcohol on that way. Maybe someone in the research has done it, but I don't think it's real common. Books don't talk about it, so that tells me that it probably isn't something that's real easy to do. Okay, so the problem that you have then is figuring out where to put your double bond. You need the double bond to be in the right spot so that when you do Markov-Nikov addition, the ether ends up in the right carbon. So let's go ahead. My druthers are to slice it right there. And I'm going to make the top half my alkene, the bottom half my alcohol. So going backwards, let's see what I would need. Just like that. And if I put the double bond there, the geometry's a little goofy looking, but if I did that, let's think about it. I would have my mercurium ion here. Right, with a plus. And the alcohol would attack right there, which is exactly where I need it to attack. So that works, right? Everyone okay with that? Okay, how about another option? Would this one work? Yeah, that would work too. So I can take either one of these and just go mercuric acetate, isopropyl alcohol, NaBH4, and I would get that. How am I going to decide which alkene to use? Which one's the most substitutable? You know, I would look, at my starting materials that I was allowed to use, whichever's easiest is what I do. Okay? So that kind of dictates your choice, whichever's easiest to form. All right? And using any of these, really, between the Williamson and this, you can build any ether that you're handed. Yeah, I wouldn't use the industrial one so much. Okay, questions on synthesis. All right, let's get to reactions, such as it exists. Ethers are inert to most reagents. So, let's give you a laundry list of things they don't react with. They are stable to base, most reducing agents, reducing agents would be LAH, NaBH4, etc. They're actually the solvent for those kind of reactions. Nucleophiles. So you can put in just about any nucleophile you want to. They won't react with it. That's because if they did, the leaving group would be this, OR minus, which is terrible. It's a rotten leaving group, so they won't react with nucleophiles. Dilute acid. Those bond things that are stable too. That's a lot of stuff. There really only are two things that ethers would react with. So they will react with oxidizing agents and they will react with hot, strong acids. And we can even change, let's see, yeah, let's leave it hot and strong. Okay. Yes?
For that first step, you did use like H2SO4 and E to get that element, right?
Oh, it depends what I started with. I mean, let's say, depends what your starting material is. If you had, let's see, there's that. There it is. Let's say I had a ER here, I use base.
Oh, yeah.
If I had an OH, H2SO4 and E.
And what if it's just like by itself? You can't get it one, can you?
If it's just by itself like that,
Yeah.
oh, what am I gonna do first? Bromination, I do Br2 and light, put a bromine there, then I can get the base. Okay, so let's take a look at the two cases where it actually does something. We'll talk about this. The oxidizing agents is the most dramatic. I don't know if you guys, you probably weren't paying any attention, but we kept the ether in the refrigerator. Remember whenever we had to grab it, it came out the fridge real cold? Notice that it was in either a dark brown bottle or sometimes in a metal can. So, talk about what you do with this. It's kept cold. It is in a metal can or brown bottle. Okay, that eliminates light. And something you probably didn't notice, but it had a date on it. Every can in stockroom, when it comes in, they write the date on it. And I think their cycle is 6 months or a year. And if the bottle has sat in the fridge for a year, it's gone. Okay, so they don't sit around. The problem with ethers is oxidizing agents cause, and let's use diethyl ether, that's the big problem that people run into. So that's your solvent, it sits around lab, and let's say you don't use it often, maybe once every 3 years. Well, the minute you open the can, you have exposed it to oxygen, which is an oxidizing agent. And any oxidizing agent would do this, but the big problem is just air comes in. And when you do that, the ether is oxidized and form what is called a peroxide. We've seen peroxide. We think of hydrogen peroxide, H2O2, right? It just looks like this. Okay. So this is the alkyl equivalent of hydrogen peroxide. So it forms peroxides. Peroxides are explosive. Yeah. They're shock sensitive. And so if you build up a lot of peroxides in the container and your ether for some reason evaporates, leaving the peroxides behind, it could be something as simple as picking the can up and moving it, and it goes and blows up. So that's why there's a date on it, so that it limits the amount of time it's been sitting around bathed in oxygen. Okay? Eliminating light helps keep this reaction down too. So that's kind of a bad aspect of ether. So if you're ever in a lab and you see an ether container that looks old and crusty, don't touch it. Seriously, don't touch it, because it can blow up in your hands, and that's really, really bad.
Take out to a field machine.
Okay? Those labs are pretty safe, and this kind of thing doesn't happen. This next reaction, I've actually had this happen to me. And usually you're not using hot, strong, or concentrated acids. It's not like a typical reaction condition, but sometimes it occurs. And the second reaction is that ethers are cleaved by hot, strong acids. And And where it happened to me, I was in a 421 lab years ago, and we used to have the students kind of do their own experiment. They would design their very, very own independent experiment. And one of the things this student had to do, I forget what he was doing, but he had to take whatever his material was, and we had it in ether, and he wanted to put acid in to cause something. So we're doing it, and pretty soon, the ether disappeared. And I'm like, that's just weird. And so he does it again, and the ether disappears. And what was going on, it was getting cleaved, and obviously it wasn't ether anymore. So this is kind of one of those oops sort of things. This is not a reaction that you necessarily would go and strive to do. This is one of those things where you're doing something else and you go, whoops, and it's one of those reactions. So let's take a look at it, and let's do, I don't know, let's do isopropyl ether. Okay. And we'll cleave it with HBr. Oh, and this is limited too. Let's HBr and HI that do this. So it's odds of this happening to you are really like not going to happen. Not HCl. And we'll talk about why that is. Okay, so we're even limiting it down even more. So I'll use HBr. And what's going to happen is I'm going to get an alcohol and a bromide. So I'm going to break the thing in half. In your book, you'll take it one step further. And the issue is with the alcohol that we make. You do make an alcohol initially, and we'll do the whole mechanism. But you've got hot, concentrated acid, and the OH reacts further, and it ends up forming this. So what you really end up with as the product is just the alkyl halide at the end. So let's go through and take a look at it mechanistically and see what's happening. All right, so I have HBr. What do you think the first step is? Protonate, yeah. One of these is becoming a leaving group, right? As it stands now, it's a terrible leaving group. So the first step, we'll protonate it, and we'll turn it into a good leaving group. Okay, there it is right there. Okay, what do you think happens next? And bromine comes and attacks. So bromine attacks, picks out the leaving group, and then I have this side is an alkyl bromide, and this side is the alcohol. And the alkyl bromide just sits there. But the alcohol, since it's being bathed in hot HBr, reacts again. So I protonate. And then Br minus can come and kick out water. And that's why oftentimes textbooks only show the alkyl halide product. But that actually involves a secondary step to get to that. All right, let's talk about the particulars of the reaction. The mechanism can differ somewhat depending on the nature of your alkyl groups. So, the reactions SN1 or SN2, depending on the R groups. When it's SN2, that is where the iodide or bromide ion that's attacking can actually get in and attack. So notice I have this attack right here. This can't be too hindered, or it can't do an SN2. So you'll see SN2 when your R groups are are primary or secondary. You'll see SN2. When the R group is tertiary, it can't do this reaction, so you'll do SN1. So if your R group is tertiary, you see SN1 reactions. So let's do another example. And let's do this one. Take a look at the products. Let's do HI. Okay. First thing that will happen is I'll make this one. And now I have some decisions to make. I have a primary R group here on this side. I have a tertiary one here on that side. My nucleophile is I minus. So what kind of nucleophile is that? Really good nucleophile. And the reaction is going to, just based on the nucleophile, it's going to want to be pretty fast. SN1 reactions take some time, right? It takes time to ionize. So for this to fall off as a carbocation, it's going to be slower. So the SN1 part will be slow. I minus is a good nucleophile. This half right here is a good SN2 substrate. And so what you're going to see mostly would be this. I and OH. It's kind of a moot discussion though, because you won't ever actually see that, right? Let's say you had something like this though. This is where you might see the mechanistic difference. What if I had something like this? And let's do, keep it simple. This can give us a mixture. I don't want to do that. Let's do this. Keep it symmetrical. Let's say I built that guy. And I treated it with HBr. Well, I'm going to initially make this propane. There is no SN2 possibility here. It's tertiary on both sides. So this will have to go SN1. And so I will have that as one of my possibilities. And then I would have this. You guys okay with that so far? Okay, it has to go SN1 because I can't do SN2. And now here's where things can deviate a little bit. If I'm using Br, right? Let's say that Br minus attacked. I would see a bromine there, and eventually that's going to turn into a bromine too, right? So I'd see bromines there. What else would I see? What would be indicative where I could tell this thing really happened? What else might I see? You always see SN1 and E1 together. I would also see some of this as well. Okay, that's it. I mean, this really is kind of an oops, because you generally do not make alkyl halides by cleaving ethers. It's hard to do. There are much better ways to do it. All right, don't pack up yet. What we're going to learn about, we'll just do nomenclature of it today, cyclic ethers. And then we won't get back to them for another 10 days, but the nomenclature is kind of fun. It's a little kooky, but sort of fun. The nice thing about cyclic ethers is they can be synthetically useful. In particular, this guy. We use that, remember our Grignard homework? We used ethylene oxide or epoxide. That's actually a useful ether once the top open. And so we're going to study cyclic ethers now. And we'll start out with naming them. Let's do that guy. 4-membered ring. 5. And I even have 6. Okay, I'm going to give you guys a couple of nomenclature systems that you can use. The 3-membered ring has a couple of names. Ethylene oxide, that's common. Epoxide, that's common as well. So those are its 2 common names. Then it could also be called, make sure I get this right, oxacyclopropane. It's a cyclopropane, but an oxygen, isn't it? Oxacyclopropane. Applying that to this, what would you call this? Oxacyclobutane. And it doesn't take too much to keep going on. Oxacyclopentane, oxacyclohexane. Okay? You may see that. You may also see this. Here we go. The oxacyclobutane is also called oxetane. And if you want to memorize these, more power to you. I don't know what they are, that's why I haven't looked at the notes so hard. The 5-membered ring, oxolane. And the 6-membered ring, oxane. They're just common names that stuck. You have to accept some. So, when you're naming these things, and they have substituents on it, let's just do a quick example. Let's say you have this. Like that. So, this is number 1. The oxygen in the ring is number 1. And then you just put on its substituents with numbers appropriately and give it its parent name. So I would go, I'm going to number this way, 2, 3, 4. So this would be 2-ethyl, 4-methyl, and then let's keep it, let's brain power, oxacyclohexane. I could also have said oxane. Okay, so naming them is really pretty easy. As far as the 5-membered ring, let's chat about that for just a minute. This is a common solvent. It's a common ether solvent. Almost every OChem lab has it in a form of a still. You go to an ether still, and they call this THF. This is its common name, THF still. A still is where it's a giant distillation apparatus, huge, like the round bottoms this big, like giants. And you put in the bottom of the still a metal, sodium, or I think we use sodium in our lab. And what that metal does is it reacts with any water that's in the ether and destroys water. So it's a way of keeping your ether really, really dry. So you turn it on, you heat it up. The ether, being pretty low boiling, comes up and distills over, and you can collect it. And because it's come out of this bath of sodium metal, it's really, really dry, so there's no water. So it's great for Grignard reactions, for example. So everyone has an ether still and a THF still. THF stands for tetrahydrofuran. That's what this is, it's tetrahydrofuran. Furan looks like this. You see where the tetrahydro comes from? Okay, I've added 4 hydrogens to it to get rid of the double bonds. It's tetrahydrofuran. Okay, and that's another common solvent. I saw a hand pop up. All right, what we're going to do next time, we can't do justice to it now, is we're going to start some nomenclature we'll tag, and then we'll do reactions.